Swayam Prabha. Digital India. Educated India.
Dear students, welcome to our next discussion on evolutionary algorithms, and today we are going to talk about particle swarm optimization. So, here is a quick recap of what we have already discussed in genetic algorithms, which was one of the first evolutionary algorithms that we spoke about. So, core concept in genetic algorithm was that it was a nature inspired meta heuristic which was based on Darwinian evolution, and we were talking about certain population of solutions that we sample randomly and then we evolve it via selection, crossover and some random mutation. We also learned that it is great for complex, non-linear, not so well structured problems, and it has great applicability in optimization when applied to infrastructure related problems. So, it was a I am giving a very high level workflow of genetic algorithms. However, I encourage you that if you are not clear with any of these terms in detail, you should visit the previous lecture and go through these terminologies once again. So, we learned that we initialize certain random population, we evaluated fitness of each solution, then we selected certain parents based on the fitness, then we did some crossover and random mutation followed by replacement of weaker solution, and we continued iteration until some convergence happened, and finally we stopped when our convergence criteria was met. This criteria of convergence could be number of iterations or percentage or even absolute change in performance. If this change in performance, howsoever we measure that, is below certain initially chosen threshold, we would say that our algorithm has converged and solutions are not improving further. But if we have already learned genetic algorithms, which is so good for generalizability to problems of different size, shape and scale, why do we need other evolutionary algorithms like particle swarm optimization that we are going to discuss today? So, here is a deeper reasoning for that GAs sometimes can be slow to converge, and sometimes they are perceived to be too random. We already touched upon this aspect when we concluded our last lecture, that although we are saying that it's a nature inspired algorithm, we are introducing these mutations can be random. So, sometimes stakeholder doesn't really see what is the connect between a real world problem and chromosomes, genes, mutations coming into picture, and also algorithmically there is too much randomness built into the algorithm, as a result of which we have been exploring other algorithms such as PSO or ant colony optimization, and algorithms like PSO finds great use in optimization, that is maximization, minimization of objective function, as well as parameter estimation in various data science problems. And it is fairly popular for continuous optimization problem. And we would learn today that once we develop a good intuition for this, how simple it is to implement, because we would be just dealing with some positions and velocities, and we will be updating these positions and velocities with help of very simple rules. And this entire algorithm is inspired by birds flocking or schools of fish that move in water in certain way. Again, word inspiration is important. It's not that we are mimicking their exact behavior, because we are not saying that all birds or all fish schools will behave in same way or something like that. So now let us look into that what this particle swarm optimization really is. So particle swarm optimization, similar to genetic algorithm, is also a population based meta heuristic which learns from the social behavior. In fact, better word here would be some cognitive behavior plus some social behavior. And here particles are the candidate solution in the search space, and they move like a group or swarm, and hence the name particle swarm optimization that comes into picture. Now, each particle in our solution space would have certain thing called as position and another aspect called as velocity, and both of them would be updated dynamically. What that simply means that with respect to time, they all will change. At each time step, we would be finding the new values for these position and velocities, and each particle also remembers quote unquote best position it has visited historically. So think about from a perspective of a bird is roaming in a particular region, it could be a farmland, and it is searching for its food or forage. If it finds good amount of food in a particular location, this bird in our particle swarm optimization is going to remember, even if it is flying all over the farmland, that where I found such a good food at last point, doesn't matter how many steps it has taken, so that it at least has some surety that if I go back to the same location again, I am going to get some quantity of food than the other location. And that is one key USP of particle swarm optimization, is the memory that it would have. Remember that in genetic algorithm, we were also talking about memory in a sense that we would not hesitate to bring back the same parent or offspring or mutated chromosome back into picture, whatever was giving us a best answer. However, the amount of memory that we were dealing with in genetic algorithms is going to be way higher, because how we are going to code these chromosomes, even if we were using binary construct or number of roads or number of lanes construct, etc. And that is one limitation that particle swarm optimization also answers, if not explicitly, at least implicitly, that it does not have such a memory overburden as a typical genetic algorithm would have for a similar construct of a problem. And we will also remember a global best. Since these particles are moving like a swarm, they are also communicating with each other. So for example, if there are two birds, bird A and bird B, bird A said that, hey, I have found some X quantity of food here. And bird B says that I have found some Y quantity of food here and Y is greater than X. So B will tell to A that that it's great that you have found X, I also have found some Y, and the quantity of food that I have located is way more than what you have located. So the global best would make A move toward the direction of B. Now, in actual algorithm, there would be multiple such particles or birds that would be communicating with each other, and that would give rise to the social intelligence of the swarm that we will try to encode in combination with the individual or cognitive intelligence of a swarm of a particle that it has learned from its relative best. So we have already learnt about this, that the inspiration comes from flock of birds, and now just putting into some terminology that we are going to consistently use in this lecture. We are going to talk about the best location of its own, and we would always represent it by the term called as P best or personal best. We will also keep track of the position which is best known, and we will keep track of with the help of G best or global best. Similarly, we will have the location coordinate of each particle. This could be in 2 dimension, 3 dimension or n dimension depending upon dimensionality of our optimization problem. We would also have velocity vector of our particle I and P best I and G best. You see that G best does not have any notation at feet. It doesn't associate itself with which particular particle, but global best is that in a particular iteration which bird found the maximum food, and we do not care about identity of that particular bird because that identity of bird is already incorporated into P best I, as that bird personal best is also same as the global best. So this is the notation that we are going to use. Here are the broad steps of particle swarm optimization. First thing is initialization. We will initiate positions of these particular birds with some random positions, let us say x1, x2, x1, y1, x2, y2, x3, y3, all the way till xn, yn and so on, and they will also have some random velocities v1, v2 and so on. All these notations will become clearer as we talk about some examples. Then for each of these initial positions, we will calculate the fitness, because we will define positions in a way that we are exactly able to measure the fitness in terms of our objective functions, decision variables. We will keep on updating P best and G best. These are the 2 points that we will explore in our subsequent slides, and we will say that new position is equal to old position plus velocity. Now you may argue that why we are not following exact vector calculus here, because we want to keep these additions simple and this is just a proxy how these positions would be updated. But remember that positions and velocities will be in the same coordinate system, so we would be simply adding them together to get them that what is going to be the new resultant for these positions, and we will keep on repeating it until any stopping criteria is met. Now let us talk about initialization, how we will do the initialization. In most of the cases, we initialize the position randomly in the given domain, because we learned that most of the meta heuristic search algorithms, they are bounded by the domain. So we will specify x minimum and x maximum and y minimum. Here also we will have y minimum, here also x minimum and y maximum, and on the other side we will specify x max and y max, and this is going to be our search domain. Here we can have this domain as larger as we want, but then you can imagine we would also need more number of particles and hence larger would be size of swarm. We can make it much smaller, but then you can also imagine that we may be at higher risk of missing the actual optimal and may be stuck somewhere in the local optimal. Again, we will initiate them with much smaller velocities. The reason we introduce these velocities to be way smaller, because we do not want our birds to be moving too fast or particles to be moving too fast in the domain that they are never able to focus on on their global best and personal best. The moment they find their personal best, their velocities are so high, they may move very far away from where they were supposed to be. So these velocities have to be kept in check to ensure that convergence happens and we are not overshooting the maxima or minima as the objective function asks for. So this is a typical notation that we follow, and in most cases we sample these positions and velocities for initialization from uniform distribution unless there is a better prior available to us. Now, once we have initialized our particles, for each particle there is a candidate solution that we will treat this each particle's xi or position as a candidate solution. So, for example, if our solution problem is of type that maximize x square plus y square or minimize x square plus y square, but this is our objective function which could be casted as max or min. This you can see that if I know x and y of each particle, I can directly plug this value into my objective function, get some answer, let us say C1. I can do it for second particle C2, I can do it for nth particle Cn, and I can see that if it's a maximization problem, I would want my answers to be higher. So, higher answers will have better fitness, and those particles would have more priority or would have more weight in the flock to be heard of, because their p best as well as they would be guiding the global best in the algorithm. And similarly, the discussion changes to the other side when we talk about minimization, that particles with lower score would have higher fitness and so on. So, for minimization, we find those particular x that yield the lower cost, and examples to infrastructure systems are very obvious. That is, we would like to minimize total cost for infrastructure design, we would like to maximize resilience, that is, we can convert to minimization by minus resilience and so on. So, concepts that we learn here generalize to both sides of the problem again. Now, let us talk about the updation. So, we would like to update the personal best first. So, what each particle does is that since it knows the score, we would say that input is passed through some function. This function in fact is our objective function. Sometimes it is neatly written, sometimes we infer what is the fitness based on what is the desirability from the system, but for these discussions we are going to talk about it as f of xi. So, p best would be, if it is a minimization problem, it would be that particular argument or value of x that makes this entire function f of xy minimum would be the p best of that particular particle that it has visited. So, if it has visited 10 location, out of those 10 location, we will always remember that what was the lowest score in all those 10 points that this particle visited. After each iteration, what we would do is that if we find fxi that is better than f p best I before, then we will update the p best location. Now, understand that we are not remembering the fitness score explicitly, we are of course relating it to the score directly, but p best I here is the location and not the fitness score. Fitness score is just is in the memory to tell us whether new position is better or worse than the previous position that it has visited. If it has visited the worst position, no need to remember that. We will simply continue our further search and not update our p best I. So, by the end of certain number of iterations, each particle would remember the best position that it has visited, and that is going to be the p best I. Now, when we put all these particles that are flocking together, each of them would have their individual personal best, p best 1, p best 2, p best n, and so on. Now, what we do is that we take their global minima and we say that whatever argument or position results in the minimum value over all the particles in the flock, that is going to be my global best in minimization problem. I always write this word maximization and minimization because some students may get confused that, hey, if something is minimization, something is minima, how it can be the best? Because the problem is of minimization. So, we want our objective function to have as lower value as possible, for example, the costs or the losses and so on. So, with this point, what we get is that it is the best among all personal bests in the swan, and note that this G best would strongly influence how everyone moves next. or it will guide the social intelligence of entire swarm, whereas P best was guiding the cognitive intelligence of individual particle. And you can see that both of them are also related because G best is going to be the subset of all the P bests considered together. Now, let us update the velocity, which also happens to be our key equation in particle swarm optimization. Let us look into various components that are involved. Here it says that new velocity of particle 1 would be existing velocity of particle 1 multiplied by some inertia. This inertia ensures that we are not changing velocities at way faster rate for the reasons that we already discussed, because we don't want particles to keep around dancing around the optimal without even waiting to stop there and see whether they are indeed closer to optimal. Otherwise they will keep on dancing everywhere. Plus some update. One update which is driven by the cognitive ability, and second update which is driven by the social ability, and mathematically we say that it is some measure of cognitive coefficient which we use as hyperparameter or a predefined value that we provide, multiplied by difference between P best I minus xi. So what it tells us is that higher is the difference between the best position and the current position, change in velocity would be the strongest towards the P best I. That is why we are simply differentiating, taking the difference and multiplying it by C1. And then, like most of the evolutionary algorithms, we introduce a small component of randomness and multiply it by a random component R1 so that our solutions do not get stuck at certain point, which may be the case when we are updating these particular weights in certain manner or too deterministically. Similarly, we have second term C2 R2, and as you can imagine, here it would be difference between G best minus xi vector. We should write this as xi vector since we are talking about particle 1. All the subscripts would take position of 1. Only thing would be R2 is the random number that we are generating for the social component. When we add these three things together, we get the PSO velocity updation formula, that how particle velocities shall be updated, and we will keep on doing it for all the particles. I can take 1, 2, 3 all the way till n. So we have already interpreted this velocity formula. So let us look into the alternate interpretation as well. That is the first term, inertia term, ensures that we continue to move in the same direction. Second term can also be thought of as a proxy of self-confidence, that how much confident about my personal best and I should be moving in the direction of personal best. And third one says that, hey, I am part of a swarm and collective intelligence can be more than my individual intelligence because I am also part of the group. So I should also weigh in the social intelligence of the swarm, and that is what is weighed in by the third term. So what it does is that, if you recall, in GA we introduced two terms, the exploration and exploitation. So here also our random factors plus inertia gives us the component of exploration, whereas knowing the personal best and group's ability to find the best solution guides us towards exploiting the knowledge that the cohort already has in the maximum possible way. So now that we have learned how to update the velocities, we have to translate these velocities to the position, because value of objective function is guided by the position, and of course if velocity is changing, position of a particle will also change. So what we do is that we simply add these two terms together, and you can think of it as a resultant at each time step, that if I am moving in certain direction, after 1 minute or 1 hour, whatever is the time unit we are talking about, my position is simply going to be previous position plus the velocity component that I am adding. And then we check that if we go outside x min or x max bound, we may clamp and reflect it back. That is, I cannot go outside the bound. So upper bounds and lower bounds are decided before we started our iterations, and after our next iterations we again re-evaluate the fitness p best and g best. Then once we keep on doing this exercise number of times, we look at the similar termination criteria, whether we have reached fixed number of iterations, or improvement is happening or not, or our compute budget or time budget has exceeded or not, and whatever solution we get, we return it as a best possible solution. Again, the reason this become meta heuristic approach is that because we may or may not get to optimal, but if we have enough number of iterations and we are searching within a finite bound, there is a guarantee. I should not use the word guarantee, by the way, but there is a high possibility that we may be closer to global optimal, if not exactly there. So a near optimal solution with enough number of iterations would be possible if we are following all these particular steps. But again, since we are not doing any differential calculus, not checking for necessary conditions, sufficient conditions, there is no absolute guarantee that that point is guaranteed to be the minima or maxima. So let me throw some light on that. What are the typical parameters of values of hyperparameters that we typically use? We also call this as a PSO parameters. First one is the weight. Typically we initialize this weight in the range of 0.4 to 0.9. If we have higher W, it means more exploration, because it will move faster in a particular direction, because it makes particle move in the original direction, and lower W means that we are giving more weight to the other two parts, which are personal intelligence and cognitive intelligence, so that emphasizes more exploitation. C1, C2 are the acceleration coefficients based on the individual intelligence and the group intelligence, and we typically take the value greater than unity but in close proximity to the unity. Again, as I said, these are hyperparameters. There are number of literature that also guides how these hyperparameters are selected, but as a first course, it may be wise or prudent to select these particular values, typically in range of 1.5 to 2, to ensure that your algorithms converge. Next comes the population size, or how many particles should be there. So typically, depending upon the size of the domain, we initiate this. In some cases, you can also have 1000 particles, but you can imagine that the data storage, the compute, number of time steps would be fairly larger. But in classroom problems, typically 20 to 50 particles should be good enough as an initial starting point. And maximum iteration really depends upon how much compute we have. But typically the value that we are going to use is going to be in range of 100 to 1000 iterations, depending upon the computational complexity. Now, in your textbooks or further reading, you may also encounter some alternate versions of mathematics of particle swarm optimization, but you need not get intimidated from that, because if the fundamental is clear that it is balancing exploration and exploitation. Exploitation consists of two components, that is social intelligence and cognitive intelligence. Other versions would be pretty much comprehensible to you. For example, one version says that rather than having velocities being updated too drastically, we should constrict it with some another parameter chi, and this chi can take value between 0.1 to 1, for example. So higher is this constriction, slower would be the updation in overall velocity. There could be adaptive or decaying inertia weight strategies. So for example, as you are moving closer and closer to your near optimal solution, you start having lesser and less inertia, and that ensures that convergence of our algorithm is faster convergence. And these problems become very particularly important when we are talking about exploration and exploitation over large domains. And these are the variants that we typically use when we are exploring over much wider areas and problem has much higher complexity. So now let us look into an example of minimizing objective function, that is fxy x square plus y square, and our goal is to minimize x square plus y square. It is very clear here that if I put x equal to 0, y equal to 0 in real domain, my answer is going to be minima. So, but we will illustrate here that how particle swarm optimization converges towards 0, 0 from some random initial points. So what we will do, this is a small problem. So rather than initiating hundreds of particles, we will just initiate 3 particles so that we can solve this problem using pen and paper. So I randomly initiate these particles at location 2, 2, minus 1, 3 and 4, minus 2, and all these initializations are happening in some Cartesian space. I would know their initial velocities also because I would be sampling them from my uniform initialization between x min, x max, comma y min uniformly between y min and y max. So these are the 3 values that I have sampled for velocities and 3 values I have sampled for the positions. So next what we do is that we do a very specific example to see that how these iterations will work. Just I think I mentioned that 20 is better. In fact, it should be other way around. Since this is a minimization problem, 8 is better than 20. So that is going to impact our solution. So if it is a maximization problem, then of course global best is going to be 20 and local best is going to be 8. So I should mention that F22 equal to 8 is the global best at this particular stage. So what we do next is that we update all these positions, that is Vi would be W times Vi plus C1R1 P best minus Xi. So since particle 1 is the local best as well as global best, the position of both local best and global best is going to be 0, 0 and 0, 0. So the velocity update is going to be 0.5 into 0.1 into comma minus 0.2, which was our initial velocity vector, plus 0, 0 plus 0, 0, because none of these particular components are going to change. Why? Because particle is already at its best, both local best as well as global best. So we get the new updated velocity as 0.05 into minus 0.1. So if you see here that we have slowed down the particle because of inertia, because particle when is already at the best among all the swarms, so it should slow down its movement and start exploiting its position to find the forage. So the updated position will change minimally from 2, 2, it will become 2.05 into 1.9. Now we go to particle 2 and find its initial position, initial velocity. We already know that the global best is at 2, 2. Its P best 2 right now is only going to be minus 1, 3 because this is the first point. We have not updated the velocity of this particular particle. Then we write the updated velocity vector in the same fashion, that is 0.5, which is inertia multiplied by initial velocity plus cognitive term plus social term. So we get to our answer as 1.35 comma minus 0.4. And after all these iterations, we see that new position of x2 is 0.35 comma 2.6. In comparison to particle 1, particle 2 has moved quite a bit from minus 1 by 3 to 0.35 comma 2.6, indicating that particle 2 should also start converging towards particle 1, because particle 1 right now is controlling the social intelligence of the group by already being closer to the minimum value in comparison to the other particles. We do exactly same process with particle 3. I leave this as a small homework, but I already give you the values of initial position, initial velocity vector. We already knew the g best. Based on that, you can check whether you are also getting x3 as 1.8 comma 2.225. Now that we are done with the first iteration, we can now find the new value of objective function, because we have moved slightly. Now if you see that at x1 we were having the original value as 8, here it was 10, and here it was 20. Because of this slight shift, 8 has moved to 7.81. 10 has even reduced below the original best. So particle 2 now, because of its movement towards particle 1 and overshooting particle 1 by slight magnitude because of the randomness that we have incorporated, has even performed better than particle 1 in finding our desired optimal value or minimal value, and particle 3 has also moved from 20 to 8.196. Remember that this is a simple problem. We already know the solution is at 0, 0. So we can clearly see that now particle 2 should control the social intelligence of the group, or what we call as should be guiding the G best. But we will also update their P best. Their old P best was 8, new is 7.81. So we will update the personal best for all the 3 particles from the values that we obtain, and the new global best becomes the position of particle 2 and the value that we are getting here as 0.35 comma 2.6. Again, we are going to use the coordinates, and we do not worry about the costs associated once we have identified the P best and the G best. We will keep on iterating in similar fashion computationally. Of course, we will not do 100 iterations by pen and paper, but we got an idea that even if we have to do 3 or 4 or 5 iterations, we should be able to do that. So here is a neat visualization that how PSO actually converges towards the solution. So here is the same problem, x square plus y square. So these are the particles, they have to go towards the blue dot, and you see that at iteration 0, I have initiated some 10 particles, all of them spread somewhere in space. Then at 10, they move towards the center, which is our blue dot. Let me highlight it a bit better. And when I iterate it over 50, you see that all particles are now masked behind that small star that I have already put, giving us a clear visualization that how PSO actually converges towards optimal. Now coming to infrastructure examples, we use particle swarm optimization for finding pipe diameters, pump locations, reservoir flows, etc. And our objective could be minimizing cost and energy usage subject to certain constraints at each node. And what we do is that we set up the particle swarm optimization problem, where we choose particles as individual pipe diameters or pump sizes, and we have large penalties, something like 10,000 multiplied by deviation from constraints as penalization terms into our model, so that we can account for constraints into our PSO models, and we'll then let the swarm converge to feasible and low cost solution as the need arises. Similar extensions exist for problems such as bridge design parameters, where we have to choose dimensions of girders, deck thickness, and we may want to minimize material cost while ensuring the load capacity. Again, a similar structure where each particle is assigned certain vectors like d1, d2, etc. And you can see that, as we saw in earlier example, these can be continuous values. We don't have to be restricted to integer, or sorry, we don't have to be restricted to certain types of numbers here, but if we understand the algorithm, we are exactly doing the same thing again and again. And finally, similar examples exist in urban transportation planning, where you could have objectives such as assigning traffic flows, finding green light times, red times, amber times, carrying capacity determination. And again, we set up the similar particle swarm problem, where particles now represent distribution of lane additions or intersection geometry. Something very similar we did in our genetic algorithm, where we said that it could be 3 lanes, 2 lanes, 1 lane, and so on. Here also we can say that x vector in the similar form, and we can then evaluate the average travel time and find the global best solution, use it as a social intelligence factor or an individual cognitive intelligence factor. But again, all of them happening stochastically, but in a very systematic manner, we would see that they would converge to some finite positions. Now let us quickly talk about this advantages of particle swarm optimization. It's a beautiful, simple and elegant concept. We just started with some positions and velocities. We do not have to worry about complex operators like crossover, mutation, which may be a bit hard for us to generalize to engineering problem, because they would of course would be strongly grounded into biological systems, but making an engineering sense of mutations, crossovers may not be that clear. PSOs converge at much faster rate in comparison to genetic algorithm, because they have randomness controlled in comparison to the GA, one of the limitations we also discussed when we were talking about genetic algorithms. And it only deals with only 3 to 4 parameters, that is W, C1, C2, population size, and everything else is happening fairly logically, that how a particle should communicate with each other. And they are very less prone to local minima than gradient based approaches, because your particles you would be sampling from uniform distribution over entire space, and you would be letting the global best guiding the social intelligence. So that gives us some immunity to get to prevent from being stuck in the local minima or local maxima. And of course, as we learnt in case of genetic algorithms, PSOs are also fairly easy to implement and parallelize. Let us also talk about some disadvantages. Remember, at the end, it is also a meta heuristic approach, so it does not really guarantee whether the point is indeed global maximum or minimum. Of course, there is some immunity inbuilt in the algorithm to prevent stagnation at one single point, but still we may also sometimes see that the swarms may prematurely converge if diversity is lost, and that is where we have to choose the parameters, that is C1, C2, R1, R2, W very carefully. Also, what happens is that since we always use single global best to guide the social intelligence, it may cause early convergence. So there are certain variants that exist that account for top 3 global bests and take their averages, or let people search for their best solution in their proxima and use that to guide their small community based social intelligence, to ensure that we are not resulting in the premature convergence. And of course, this remains the golden assumption for everything that surrounds heuristics or meta heuristic approaches, that like most of these, it's an approximate solution. So here is a quick key takeaway for us in terms of discussion that we had today, that PSO is a popular fast converging method for continuous optimization, and P best, G best and velocity is the essential core of the algorithm here, and it finds great application in water system, structural design, transportation and risk minimization applications. There is a huge body of scientific literature that has used PSO since their origin, and also, as I mentioned earlier, parameter optimization in data science is also a great application of particle swarm optimization. So I encourage viewers and listeners to explore these literature on their own, and you should be able to relate to the mathematics that we have already learnt and apply similar methods to their use cases. But as you are implementing, make sure that you account for these bounding boxes very carefully, use various parameters including balance of weights, social and cognitive intelligence properly, and check feasibility constraints via penalties or some ways to specially handle them carefully. So, now we can conclude this particular discussion. We have already learned about GA and PSO. Going forward, we will have discussion on another very interesting approach, what we call as ant colony optimization, which is also widely used for decision making in infrastructure systems. So, thank you. Dear students, in our previous lecture, we looked into the theory of particle swarm optimization, a very powerful heuristic method for optimization, and we understood the mathematics, the formulae behind that. In today's lecture, we are going to see one small example that how to bring PSO in action using programming. Today we are going to see this particular example in Python. However, you are free to explore other programming languages by following the similar logic structure. If you recall, we learned that when we are dealing with various optimization decisions in the context of infrastructure, for example, here our decision could be this placement of new water treatment facility or design of roads or expansion of power grids. These problems typically involve nonlinear cost functions, for example, land usage, construction cost, environmental impact. There are multiple budgetary constraints, regulation constraints and environmental limits, and there are large decision spaces. For example, this problem could be posed as over an entire city, find the optimal location to find where water treatment plant or some wastewater treatment plant should be constructed. That is where we go towards the approaches such as particle swarm optimization, which we say is a nature based optimization method that can handle several complex search spaces without requiring any gradients or derivatives that have been powering lot of other algorithms that we have looked. Also, in these cases, we cannot use simplex method because neither our objective function is linear nor our constraints are linear, as a result of which we may have to go towards a non-linear optimization approach. And if we are looking for an approximate answer or near optimal answer, we often go towards the heuristics. So now let us try to understand this example with help of a storyline. Here the problem is that we want to find the optimal location to build a new water distribution center. Now, this is a city which would be having some bounds, and here we want to find some interesting way that where this center should be. So, what we will do? We will take lot of particles. We may call them insects, birds, drones, whatever we want to say them, and we will leave these particular particles over an area so that they fly and they search where should be the best location. Now, all these particles, they are going to observe and communicate amongst each other. What they will observe? They will observe that what is their personal best experience, that is where they find a particular site with lowest cost or higher suitability. These particles do not have any ego conflicts among themselves, so they also communicate to each other to know where other person's best may be. So, they would also be having information about the best experience of any particle that is hovering over this entire city. And this city is of course going to be confined by a geographical constraint, which is going to be our domain where we are going to search for the solution. And finally, what we will see that all these particles or swarm of particles will finally converge towards a promising region, which help us decide the best site. With almost surety, we would see that the best site is going to be in that particular region. So let us try to look into this specific example with help of a function in xy domain. I have generated a very well known function called as Eckley function, which is a two variable function, but here you would see there are some terms of exponential. Within exponential we have square root of x square plus y square, then there are some cosine terms, then there is another e term. Now you can imagine that if you have to take the differential of that and then perform the Hessian test, etc., it is going to be fairly cumbersome. Not that we cannot solve it, we can always solve it using exact methods, but here our objective is to test the PSO on some complex function that we have generated here. So we already know that this particular function has global minimum of 0 at xy equal to 0 comma 0, but our PSO would not know anything about it, and we will try to see that by simulation or running this heuristic method are we able to reach 0 comma 0 in finite number of iterations. Note that in a real world system you can always take a different form of objective function xy, be it single objective, be it multi objective. For example, in case of infrastructure project, you may have the construction cost as a cost, maintenance cost again as a cost, and benefit is a gain, so it represent negative of a cost. So your objective function in xy could look something like construction plus maintenance minus benefit, and this xy, f of xy can be replaced by some mathematical form of function that you may have here. So now what we have to do is that we have to apply the mathematics that we have already learned about particle swarm optimization, where each particle would have a position, a velocity, a personal best position, and a swarm keeps track of the global best. You see that we have learned all these terminologies into the mathematics, where first term also represent that its own velocity vector, where W is the inertia weight that also makes a particular particle move in the direction in which is already moving. Second one is updation using the personal best, and final term C2 R2 is the updation using the overall best. And these R1 R2 are some random numbers that we sample from a uniform distribution between 0 and 1, and this ensures that our algorithm is never stuck at certain point, and this ensures that our algorithm has enough opportunity to have some element of stochasticity to come out of the traps of local minima and so on. And finally, we will keep on updating the position that at new point xt plus 1 it is going to be xt plus the velocity vector that we calculated in this particular way. So xit is also a vector, velocity is also a vector, we just update it and we get our updated answers for the new position. Note that this is a bounded method, that is we are searching for our solution in a given domain, -5 to 5 in x axis, -10 to 10 in y axis and so on. So if we see that our new position is outside the bound, we will clamp this position back to the boundary of our solution. So here our first step is of course to define the objective function. We have already defined the Eckley's function. In real life it could be a more complex function. Then we have to initialize the swarm, where these swarms are going to be some scatter points with some location x1, y1, x2, y2, x3, y3, which again are vectors, and we will initialize their velocities to very small value to begin with. Sometimes you would also see a zero value initialization for all particles, but there we always run at a risk that certain particles may not move at all. So practical advice is always to initialize them with a very small initial velocity, then 0. And then we would be writing one main loop where each particle's velocity would be calculated using the equation above. Then we will update the position, we will keep on checking for the bounds and so on, and then we will at the end of each iteration we will be calculating each particle's fitness. We will update its local best and we will communicate the global best to all the particles, so that we balance the cognitive intelligence with the social intelligence as we discussed in the theoretical part. And we will keep on iterating it for some number of iterations, and finally we will create some interesting plots. Here I will be using a GIF plot where you would be able to see the animation, that how these particles converge to a particular point, and then we will try to interpret the results that what we observe here. I have tried to write this particular code with all the comments elaboratedly. I understand that many of you are watching this particular episode on television, but idea here is to get the understanding how these algorithms are built, how they are put together rather than worrying about the exact syntax or codes, etc. I will go through each of the part of the code, each block bit slowly, so that you understand what each block is doing. As you recall, whenever we begin any programming or any coding in Python, our first block of the code is always to import few libraries that we are going to use throughout the exercise. Here I am going to use some very basic libraries, for example NumPy, which would help me deal with the matrices. I am going to do some plotting here, and I am going to also build some GIF. So there is an inbuilt library called as image IO that I am going to use here. If it is already installed on your computer, you can always comment this line by using the hash. However, if you do not have not installed or you are just starting a fresh work environment, it's better to install that. In my case, I have already installed that, so I will just comment this particular line. Now our next block represents definition of the objective function. Here I am using ACLI function in x and y. So I define all the parameters a, b, c and write the function that various terms are there, and whenever I would execute ACLI function or call ACLI function with given values of x and y, it should give me sum of all the individual terms which represent the value of f of xy. Now my next task is to set up particle swarm optimization. I have to give some random seed. Number of particles that I am beginning with are 90. If your objective function is very complex, you can also start it with 500, 300, 400 particles depending upon complexity of the problem and compute you have. Maximum iteration is again a hyperparameter. If I see that convergence is happening, I can use up to 50 to 100 number of iterations. Again, if objective function is too complex, I can have perhaps 100 iterations, and then I also specify the bound that my solution in x domain is between -5 and 5 and in y domain is -5 and 5. Note that in this case I know that my answer is 0, 0, so it is a good domain to have. However, sometimes this is also an iterative search, that if you will try with multiple domains, sometimes based on physics, sometimes based on a random sampling over the domain in which you are searching for the solution. So here our life is bit easier, but this also is one of the limitations that we have discussed in PSO, that if we are way off from the domain of search, we may get non-optimal answers, or we may confuse local minima for the global minima, but it is nowhere closer to any of that. And finally, as I said, I will initialize some positions. So I will have these positions here between this domain, as well as velocities would be specified, and as I will store all these numbers into a vector. So for each particle I have x and y. That's why I have n comma 2, n number of particles, each particle having two attributes, x coordinate, x ordinate and y ordinate. Similarly, when I go to velocity, I have velocity in x direction and velocity in y direction. So it really depends on dimensionality of your objective function. If you are dealing with an objective function in which may have 7 decision variables, you can quickly see that how this initialization would change here in terms of number of variables that you are going to use. Then I am also going to have this personal best, where I am going to save the personal best and its value for this function, and this is where I am measuring the performance for p in position. So here for each p I am going to calculate ACLI function value, and I am just going to take best of the value that I would get here for each particle. Similarly, I would also do the global best, which is the minimum value for all the personal best values, and this value would be told to all other particles. Then I also have some parameters W, which is inertial weight, C1, C2, 1.5, 1.5 each for the cognitive intelligence and social intelligence, and at each point I am also storing the history, that where particle went, when it visited there, what was the personal best for a particular particle and what was the global best for the entire society that they are doing. Once my entire particles are defined, all I have to do is that run these iterations. Here you see that I have defined maximum number of iterations as 70. So I will be iterating over entire code block 70 times, and this is the same formula that we earlier saw, that velocity is updated as W is equal to V is equal at t plus 1 is W into Vt plus C1 R1 P minus X C2 R2 G minus X. Now if we go back to the code that I have highlighted, I have just coded the mathematics that I have written earlier, W into V plus C1 R1 P minus X C2 R2 G minus X. Now only thing is that I am using the Python notations to write my formula than the mathematical ones, and then I update the position. New position is equal to old position plus the velocity, and I would ensure that every time positions are clipped if they are going out of the domain, and then I will evaluate the value of new fitness as it moves to the new value. If the new fitness is better than the previous fitness, in case of minima, if the new solution is lesser than the previous value, I would update the personal best as well as the global best using the same logic. If you see, I have put some if conditions in check. That is, if this happens, only then global position is updated, otherwise we continue with the same global update. Rest of the lines, I want to of course create multiple frames. That's where I was using operating system library, which gives me access to the folders and files in the computer, but I would not worry about block 4 to 5 as of now, because here I am just generating the code, running the code and generating some plots and creating a GIF file, which is bit of an advanced concepts in Python. So let's not worry about that, but let us run this code and see how much time it takes. So now it is running. It should not take much time, but it also gives us time to absorb some of the things that we are discussing. As soon as the code compiles, we should be able to see an animation somewhere here. Yeah, you see that now animation is up. All these particles started from somewhere. By 70th iteration, they are all dancing around some one small point. I can of course increase the number of parameters. So I can, let us say, make it 150, run the same code again. Whenever I press this press button, it of course will take some time. Larger are the number of particles, more time it is going to create. But I can see that it is not turned red. This radio button has not turned red. That means there is no error in the code. It is compiling. It started just 1 minute ago. Perhaps in couple of seconds we should have results. Here you see, if you have more number of particles, convergence is even faster, because now global best is getting searched in the larger domain. So now I hope that this gives you a very strong intuition that how particle swarm optimization works both in theory and action, and I expect that many of you are going to explore its real world application to optimization problems, both convex, non-convex, linear, non-linear. Thank you.